We're going to continue our conversation about sine, cosine, and tangent. It's important that we discuss more characteristics about these graphs. Uh, and then we're going to tie it back to the unit circle and talking about generalizing our solutions. So here's what we're going to do. Yesterday we talked about the domain, the range, as well as the y-intercepts. There's one more thing we need to discuss. So we're just going to take a look at each graph and describe stuff. So I just typed these into Desmos, and I want to hide the graphs because I don't want to look at it right now. So this view doesn't really help me. Like, it's in radians right now because if I click on this little wrench and hide my camera, click on the wrench, we see that the radians is highlighted. However, for my step, I kind of want my x-axis to be in terms of pi. So I'm going to say pi divide by 2. And all I did was just type in the word pi. Hit projector mode, okay. And let's have this go by 1. Okay, yeah, I like the way this graph looks. So, if you notice, this sine graph oscillates forever and ever. If I zoom out, it keeps oscillating, keeps oscillating, keeps oscillating, and well, you're gonna kind of get the drift. But it keeps oscillating between the same two values. So if we remember the range for sine, and actually let's make that red because we're talking about sine here. Sine has a range from -1 all the way to +1. Right? And it oscillates between those two values forever and ever. So we're going to talk about something called the period of the graph. Period. So right now we know that we typically have a y-intercept at 0, 0. There we go. And I'm going to draw another imaginary line here. So I would say the period for sine is 2 pi. During that time, the graph goes from 0, 0, it reaches its maximum, it decreases until it hits its minimum, then it continues to increase until it's right back to 0, 0. So that is one complete cycle for the sine graph, which is why we, I guess, call it the period of the sine graph, because it completes a cycle in that span of time. So that means that everything that happens, that will ever happen to a sine graph, is encapsulated in this little snapshot of the graph. So if I go backwards in time, so instead of going from 0 to 2 pi, we go from -2 pi all the way to sine. Notice, I start at 0, 0, and I go up to my maximum, come back down to my minimum, and then repeat and go back to 0, 0. That is the exact same behavior that happened over there. So if I can generalize what happens in one iteration of the sine graph, then I can go ahead and talk about what will happen everywhere else. So let's go ahead and erase all this. Jump cut. Now we're going to take a look at, instead of sine, cosine. So cosine has that same kind of oscillating behavior as sine. I guess that's why they called it cosine, because it's so similar to sine. So now we're going to go ahead and describe some behaviors that we know about sine. So we know sine has a range of -1 to 1 as well, and it has a y-intercept at 0, 1. Okay? So my goal is to try to figure out the period for the sine graph. So I'm going to take a look at its y-intercept, and I'm going to consider that the starting value. So I notice that my graph starts at its maximum. And the idea for the period is that within that span of time, I need to make sure I capture all the possible activity that will happen to this cosine graph forever and ever and ever and ever and ever and ever and ever. So here's what I notice. I start at a maximum, and then it decreases to a minimum, and I need it to come back to the maximum. So that's where my cycle kind of ends for this graph. Start at a maximum, go to your minimum, come back up to your maximum. That's what you should know about the cosine graph, right? And the idea is that if the period is 2 pi, that means that every instance of 2 pi, I should have the same sort of behavior where I capture, like I end up right back where I started, is how you want to think about it. And in the fact that I start and end at the same spot, I should be able to capture all the oscillations that will ever occur in this graph. So over here, start at a maximum, go down, decrease until you get to a minimum, start to increase until you get back to your maximum, all the oscillations captured. So sine, oh, you dummy Rodriguez, that's a cosine. How many of you guys saw that? Good for you. So cosine and sine both have a period of 2 pi. They both have a range of -1 to 1. It's just a matter of they start at different locations and end at different locations. So now let's take a look at tangent. Jump cut real smooth now. Okay. So for tangent, it's a radically different graph from sine and cosine. So you can right now, as I set up, conjecture, what do you think would happen to the period of tangent, right? Just looking at this, what do you think it would be? So for tangent, which is, I guess, green enough, its range is from -infinity to +infinity. It has a y-intercept at 0, 0. Okay. So I need to consider the period. And again, in the period, that should be from wherever I start to wherever I end, I capture all the behavior that seems to repeat itself for this graph. So I notice that right here, I have an asymptote. So I start all the way at -infinity, increase, cross through the y-intercept, keep going, and zoom off to +infinity. So then I come across another vertical asymptote. And then after this second vertical asymptote I drew, I start at -infinity, increase, and shoot off to +infinity. Then I get another vertical asymptote. Okay. And if you get my big head out of the way, you'll see that we get sort of the same behavior occurring after this third vertical asymptote. So how often does this repetition occur? If I go from -pi all the way, from -pi divided by 2 all the way to pi divided by 2, that period is pi. Now I would say make sure you jot down what the periods are because we're going to revisit them in the second video. This is just to kind of make sense of what's going to happen in the next part. Okay. So that's all you need to know about the periods of these trig functions for now.